Here is the second slide on the Chapter 8 material, Section 3 and Section 4. Just as a reminder, I'm going to just go ahead and go through the video, so if you come across a slide with a problem that you would like to work out, you're going to have to pause the video to give yourself some time to do that. So Section 3 starts off talking about solubility. Solubility is the maximum amount of solute that dissolves in the solvent at a given temperature. So if you wanted to know the solubility of a particular solute, you could go ahead and look that up in a table of solubilities. If you have an unsaturated solution, then it does not have the maximum amount of solute dissolved in it. But a saturated solution does contain the maximum amount of solute. It can't dissolve any more. Usually you have some solute left on the bottom of the test tube or the beaker just to let you know that no more is going to go into solution. It is possible to have a supersaturated solution. We did that in the lab where we made our borax crystals because and so it had more than the maximum amount of solid dissolved in it because we had a hot solvent that dissolved a certain amount, and then when the solvent cooled, it cannot dissolve as much solute, but it still was dissolved until it crystallized out. So right before it crystallized out, the solution was supersaturated. It had more than it could dissolved in it. So as we saw with the borax, many solids are more soluble in hot solvents than they are in colder solvents. However, for gases, they tend to be less soluble in hot solvents because when you heat up a gas, remember the gas molecules, they move around more, they expand more, they have more pressure, and they want to escape from the liquid solvent. Henry's law tells us that increasing the pressure of gas over a liquid will force more gas into the liquid and make it more soluble. The solubility of the gas in the liquid is proportional to the pressure of that gas over the liquid. So that's why, for example, cans of soda and bottles of soda are pressurized because it gets more carbon dioxide to dissolve in the liquid. All right, in our previous lecture, we were talking about ionic compounds and how they dissolve in water because water is a polar solvent and likes polar and ionic compounds. However, there are some ionic compounds that bind to each other so strongly that they don't dissociate when they are put into water, and so water does not dissolve them. So there's a few examples in your textbook of ways to tell whether a salt is soluble or not. They list some salts as being soluble if they have lithium or sodium or potassium or ammonium as the cation. Nitrate and acetate anions are also very good for solubility. Bromine, chlorine, and iodine are good for solubility except with a few different cations that bond them too strongly, like silver, lead, mercury. In contrast, a lot of salts that have anions such as carbonate or sulfide or phosphate or hydroxide are not as soluble. So instead of looking at the different tables and rules that the textbook has to memorize the solubility of different ions to figure out the solubility of salts, I'm posting a solubility chart online, and I will have a copy if needed for different homework assignments or quizzes. And so what you have to do with that chart is to look for the anion along the top line. There's the top row has anions, and then on the side there are cations, so you would follow it down until you have the cation in the chart. And where they meet, there's a box. If that box says I, the compound is insoluble, and so it will precipitate out as a solid. If the box says AQ, then it is soluble and it will stay in aqueous solution. So if you would like to watch this video again when you have a copy of that chart, we're going to use it for some of our problems coming up in the lecture. So here is an example of how we can use that to practice. We'll predict whether the following compound will form a precipitate when mixed. And if so, we'll write the net ionic equation. So there are two salts here on the left side of the arrow. And when we mix them, what they can do is a double displacement reaction. They can swap partners. So the first thing to do is to do that and get them to swap partners. And you can pause it if you want to try this at any point in the slide. But I will go ahead and go through that the potassium now has the nitrate and the silver now has the sulfide. And so then we'll look those two compounds up on the solubility chart, and we can see that potassium with nitrate does stay in solution. It is soluble, it's aqueous. But the silver with the sulfide has an I in the box. That means that it's insoluble and will precipitate out as a solid. And so we will write the net ionic equation by just writing what happens to form that insoluble silver sulfide. And so what is happening to form that silver sulfide is that two silver ions are coming together with a sulfide ion and forming an insoluble precipitate of silver sulfide. So here is a summary of what we did to get that answer. We did the double displacement reaction, and then we checked the solubility of the products, and then if we find something insoluble, we write an equation just with the ions coming together to make that solid. All right, so there are several different ways that we can talk about the concentration of a solution numerically. So one way is mass percent, and mass percent means grams of solute over grams of solution times 100. So don't forget that's grams of solution. If you're only given the grams of solvent, you have to add that to the solute to get the total weight of the total mass of your solution. So go ahead and try this calculation. If you have 1.25 grams of sodium chloride in 48.75 grams of water, what would the mass percent of that sodium chloride solution be? And plugging those numbers into the formula gives us 1.25 grams of sodium chloride over a total of 50 grams of solution. We add the sodium chloride and the water to get the solution, and that gives us a 2.50% sodium chloride solution. If you are dissolving a liquid in another liquid, it might be more convenient to calculate the volume percent, and that is the milliliters of solute over the milliliters of solution times 100%. So again, if you have solvent, you have to add that to get the volume of solution. So we could go ahead and try if we have 14.5 milliliters of ethanol dissolved in 85.5 milliliters of water, what would the volume percent of that solution be? And so plugging that into the equation gives us 14.5 milliliters of ethanol in 100 milliliters of solution times 100% is a 14.5% volume-to-volume ethanol solution. All right, so one last way that's probably not as common, but you can do a mass-to-volume percent of your solution. In this one, you can't really be given the solvent because you can't add the milliliters of solvent to the grams of solute and be able to calculate the milliliters of solution properly. You have to be given the volume of solution and the grams of solute, which we are below. If you dissolve 11.5 grams of sugar in enough water to make altogether 150 milliliters of solution, what would be the mass to volume percent? And so we would just plug those numbers in. 11.5 grams of sugar divided by the 150 milliliters of solution times 100% is a 7.67% mass to volume percent solution of sugar. And then the final way that your textbook gives of calculating concentration is molarity. And that is abbreviated capital M. If you see a capital M on a bottle in lab or in a problem, what that means is moles per liter, moles of solute per liter of solution. And so you've probably seen it around. It's a very common way to denote concentration because it relates moles to volume. And so moles is how we do chemical reactions. And so chemists really like the molarity concentration. Let's see if we can calculate one. If we dissolve 11.5 grams of sodium chloride in enough water to make 250 milliliters of solution, what would the molarity be? So the first thing we need to do is figure out what we have. We're given grams of sodium chloride and milliliters of solution. We need to convert this to moles per liter. So the first step, using the formula mass of sodium chloride, converts the grams of sodium chloride to moles of sodium chloride. So you have moles of solute in the numerator. And then the next step we need to do is convert the milliliters that we have in the denominator to liters, so that we have liters in the denominator. And that gives us 0.787 moles of sodium chloride per liter of solution, which can be written 0.787 molar sodium chloride. So these concentrations are a way to relate the amount of solute and the amount of solution. So we can use them as conversion factors. So for example, if we have a solution, we're trying to figure out how many grams of sodium chloride we can get if we evaporate 43.2 grams of a 12 mass percent sodium chloride solution. So the 12 mass percent means that we have 12 grams of sodium chloride in every 100 grams of solution. So that's what the mass percent is telling us. So if we have 43.2 grams of solution and 12 grams of sodium chloride in every 100 gram of solution, we can use that as a conversion factor and figure out that we would have 5.18 grams of sodium chloride in the 43.2 grams of solution that we were given. And if we evaporate it, we should get 5.18 grams of sodium chloride. All right, so here is one with molarity, molar, 2.7 molar hydrochloric acid solution, and we want to know how many milliliters of this solution we need if we want to do a reaction and we need 0.360 moles of hydrochloric acid. So what we need is the 0.360 moles of hydrochloric acid. And so if we divide this by the solution concentration, we'll get rid of the moles of hydrochloric acid and we'll have liters of solution, which is a volume, but this question specifically asks for milliliters. They want the volume in milliliters. So we have one more step, multiplying by a conversion factor that will change liters of solution to milliliters of solution. And what we would need to get the 0.36 moles of hydrochloric acid is 133 milliliters of this given hydrochloric acid solution.